Hello and welcome to another edition of Spatial Awareness. It's comet time again. It's comet time every month at the moment. Joined this month, Chris Lintott's back. Hello, Chris.
Hello there.
And as well, Alan Fitzsimmons, of course.
Hey.
So we'll talk a little bit about the Rosetta and Philae lander, and then go on to Ceres and New Horizons, the dwarf planet, and trips like that. So, Alan, we had in November, last time we spoke to you, you were on the top of a mountain in Chile.
Oh, yes, that's right.
Yes, observing comet 67P Churyumov-Gerasimenko, and you were taking observations in preparation for understanding the comet from the ground. Did you find anything useful, relevant to the landing, or was it more general than that?
It was more general than that, actually. It's part of the monitoring program we've got on Earth to follow the large-scale evolution of the comet. And we could certainly see the dust tail forming very nicely now in those images. And we're still analysing the data because what we want to do is try to see whether or not we can detect any of the gas that's been released from the comet in the spectra that we obtained. However, those are all the data now we've got to go on from Earth because the comet's now moved too close to the Sun to easily observe using optical or infrared telescopes, and we're not going to be able to pick it up again until next July. So we can sit back a little bit and work on that data now, and leave the rest of the work to the spacecraft guys.
And speaking of the spacecraft guys, of course, we had in the middle of November, I guess one of the most exciting events of the last few years, this landing on the comet. And Chris, you were there in mission control, watching it all go on. It must have been incredible to be there.
It was. I've just about recovered. I have to say, beforehand, people were talking about comparisons with Apollo, and I think it really lived up to that, most because of what went wrong as well as what went right. You know, we had what we thought was the landing, and then we realised it had been bouncing, and then there was the cliffhanger at the end of the first day about whether it had indeed come to, and then of course the 60 hours, the dash to get Philae's scientific results back to Earth. We even got a nice sense of closure at the end of what felt very much like living a movie, where we knew that all the data that the lander had been successfully returned to Rosetta from them, and there were some happy scientists, who was out. But on the whole, it was a huge success, of course, but it was the drama of it that made it exciting.
Yeah, they said that they got about 80% of the science they wanted to get, I believe, which is fantastic for such a roller coaster event. So all credit to the instrument teams who must have been working around the clock. I spoke to one of the instrument members of the Ptolemy team, the team members of the Ptolemy instrument, who said they were, I don't know, I think they slept much for.
No, I thought they didn't. I think the biggest miss, if we've taken a strangely negative tone, for which I'm sorry, but I guess the one thing you would have really wanted if you could have got it was the drill to have successfully taken samples. And I think it's pretty clear now that although the drill was deployed and retracted and moved successfully, I think it's pretty clear now that it didn't manage to get much of anything. I haven't seen that formally confirmed, but so we don't have that sample. But instruments like Ptolemy did get a good look at sort of the close coma. I don't know if that's how you'd describe it, Alan, but the sort of atmosphere of the comet. And we know that they found organic molecules in there as well. See, they're still working on the details. Obviously, they're still working out what's there and what isn't. But the ground truth data compared to Alan's observations seems to have been obtained, and that's very exciting. We also had instant destruction of the one handy science hook that we'd all been using in the press to explain why this mission was important. Of course, this mission is important because we want to understand, but we'd all focus on the fact that it's possible that Earth and Rosetta would, in some sense, provide a test of this, or at least it would test whether Earth's water could have come from comets like Churyumov-Gerasimenko. And we now know that that's not true. The evidence is that the water on 67P is rather different from the water that we have here on Earth. And so this is an exciting, if not hugely surprising, scientific result. but leaves us in the slightly awkward situation of appearing to have resolved the major science question of the mission already. Yeah, maybe we should have talked more generally about how interesting comets are.
So Alan, the question of this water composition, it has been the first big science result out since the landing. Although the result is actually from the Rosetta spacecraft itself, rather than the lander, from one on the instruments there studying the gases around the comet. And this is all to do with the composition of the water itself. So there's different. You can think of there being different types of water. Can you explain heavy water in relatively simple terms for us?
Yeah, sure. Well, so when we sit here on Earth and we put water in our coffee that we're drinking at the moment, most of that water is composed of molecules of H2O, two hydrogen atoms and an oxygen atom joined together. Now, most of that water is H2O, but about 1 in 70,000 molecules is slightly heavier, and it's because one of the hydrogen atoms has been replaced with the deuterium atom. So it's actually just a natural thing that 1 in 70,000 water molecules on Earth is actually HDO, not H2O. But the important thing is that that ratio, we think, is locked in and at the formation of an object. So if we want to find where Earth's water came from, then we need to identify some other population of objects out there in the solar system that could have brought it here. Many comets, many bright comets, have had this ratio of HDO to H2O measured in the past. But that's never given the same result as Earth's oceans. And we think the reason for that is almost all of those comets, or certainly all the bright comets, have been from the Oort cloud. So it was thought that, okay, so maybe Oort cloud comets did bring water to Earth in the early days of the solar system. Maybe it was the comets from the Kuiper belt, the so-called Jupiter family comets, of which 67P is one. And so there were great hopes that Rosetta would go there, measure accurately what this ratio was, and show it's the same as Earth's water. The problem is it didn't. In fact, it saw it was even higher than in Earth's oceans than Oort cloud comets. Oort cloud comets, there's a bit of uncertainty, but they tend to be about twice as rich in heavy water to normal water as the Earth's oceans. 67P has 3 times as much heavy water as Earth's oceans. So, so it looks at first glance that comets like 67P could not have brought water to Earth. But as usual in science, it's not that clear cut. And the reason being is that in 2010, the Herschel Space Observatory observed another Jupiter family comet that we believe came from the Kuiper belt, and that appears to have definitely had the correct relative amount of heavy water to normal water. And you've got it on that graph there, if people can see it, it's 103P Hartley 2, the target of the Epoxy space mission. So what this seems to be telling us is that, although we've only got 2 or 3 data points, that Jupiter family comets can have a range of ratios of heavy water to normal water, or deuterium to hydrogen. And what that means, we've still got to sit down and think about it. But one thing it could mean is that the Jupiter family comets themselves may come from a range of different regions in the primordial disk when our solar system was first forming, that haven't just been out there in deep freeze at the Kuiper belt all this time.
And what this tells us essentially is that comets are messy and comets are confusing, right? They don't fall into these 2 nice categories of Jupiter family comets that formed out in the Kuiper belt and have moved slowly inwards, and then Oort cloud comets that formed closer in and then moved outwards. And while, I mean, if I put the graphic back up again, we can see that you mentioned these Jupiter family comets here have got this similar ratio, and 67P has this much higher ratio, so maybe they're different. The Oort cloud comets, which are in the dark pink, also have quite a wide variation of values there.
That's right, although I mean the uncertainties are large with those, because almost all of these, apart from Comet Halley, of course, which was visited by spacecraft, all of those tend to have larger uncertainties, but they average out about twice as much heavy water as we'd expect. But this idea that Jupiter family comets like 67P may have a range of different origins, or at least they've been made of different materials, isn't that new. Originally from when the Stardust mission passed through Comet Veal-2 and brought samples back to Earth a year or so later of the comet dust, subsequent laboratory analysis showed materials originated from a wide range of distances from the Sun, from very close to the Sun to very far out from the Sun, and it all seems to have somehow come together to form this particular comet. At the same time, we know from ground-based studies, Earth-based studies of Jupiter family comets, that a small fraction of them seem to have different ratios of ices in their surfaces compared to others. We still don't know what that means, but if we manage to put all this stuff together, we may end up with a clear idea of where these comets actually do originate in the solar system. The one problem we have, however, though, if we go back to it, is that if you assume that Kuiper Belt comets or Jupiter family comets have this range of deuterium to hydrogen, then it's not clear that if we smash them all together and bring them to Earth, we end up, or we can end up, with the right amount of heavy water in the Earth's oceans. So we may have to look elsewhere for an origin for Earth's water.
And there is another origin out there, because while we think of comets as being the dirty snowballs or the snowy dirt balls, whichever way around you consider it, of the solar system, and therefore being very, very heavy in ice and therefore water, there are also objects out there not as far out, or not formed as far out, in the outer asteroid belt, to be like, sort of the outer half of the asteroid belt, which are also, I mean, up to half of them can be made of water and ice anyway, I believe. I mean, those are pretty water heavy as well. So things like Ceres and not so much Vesta, it's a bit far in, but these outer objects could be another solution, right?
That's right. And in fact, of course, we've found, as you say, these main belt comets in the recent years, which appear to be these icy asteroids where there's been a recent collision which has exposed subsurface ice, which then can be released to give the appearance of a very weakly active comet. Our problem is that at the moment we don't have the technology to measure the D/H ratio in those objects from Earth, although samples of meteorites from the outer solar system do indeed have the same ratio of heavy water that we would like to see to identify the source of the water. The important thing there is that we're going to need another spacecraft mission possibly, but that will be a long time coming, so it's a little frustrating. But of course the whole point of this is that Rosetta is revealing new stuff. It's telling us we're not as certain as we should be about the early evolution of the solar system and the origin of these short period comets, these Jupiter family comets. We really need to go back to the models and look at it, and that's exactly what Rosetta was designed to do, to not only tell us how these things work and show us, or give us more clues into the origin and composition, but if you like, it's expanding our knowledge of our ignorance as well. And I think it's done that pretty well over the past week or two.
It certainly has, and one of the things we should point out is that although the Philae lander went into hibernation at the end when its batteries ran low, there is hope that when the bit of the comet it's currently on comes into sunlight in a few months, maybe April time, that it will wake up again and will have another lease of life of the lander as well. So the mission scientists, from what people say, are quite confident that's going to happen, I believe.
Yeah, that's right. So we know Philae at the moment is somewhere in the, let me hold this up here, it's somewhere in the head region of the nucleus around here. It bounced over 1 kilometre from where it originally landed.
And that thing's only about 4 kilometres long from one end to the other, right? So
that's right. It's quite a hefty bounce. And it did a number of other things on the way. It clipped something, so it started tumbling at one point about an hour after the first touchdown, for example. It may have clipped a cliff or something, and so on. Anyway, the things that we know where it is at the moment, it only receives 1.5 hours of sunlight per comet rotation, and that gives it about 3 watts into its batteries. it needs at least 5 watts to boot up, so it can't actually do anything at the moment. But we've got 2 good things about the comet. First of all, it's getting closer to the sun, and by March, April next year, there'll be twice as much sunlight falling on those solar cells as there is now. The second thing is that at the moment the comet's in kind of northern summer, so we're seeing all the activity from the top of the comet here, but we're not seeing much from the bottom. In fact, the bottom's pretty much almost in shadow. But as the comet approaches the sun in spring and summer next year, the comet will start going and approaching and passing through the comet's equinox, where the sun's over the equator, where Philae is. And so that's also going to diminish the shadows and increase the amount of sunlight it gets. So I'm not surprised that the lander scientists and engineers are fairly hopeful that Philae may be resurrected. We just have to wait and see, because the big unknown is how the batteries will do, having been in deep freeze effectively for several months. But they should be okay. I mean, fingers crossed, we may get a signal from Philae next spring.
And of course, it was designed to do this. The lander was designed to go into hibernation and then wake up again. They were hoping it wouldn't necessarily be for quite as long. But the other benefit is that being in the shadow of a cliff, it won't get quite as hot as it might do otherwise. And also, they might be slightly protected, so they might even be able to last even longer and have the lander last for a good few months after it wakes up. So, as Alan said, fingers crossed about that. Now, the 67P is not the only object that's got a spacecraft that's going to be around it next year. There are 2 more missions that are going to dwarf planets in our solar system. So we can stay in the inner solar system if you like. Let's stay with the asteroid belt, and something we mentioned earlier. So Ceres, the largest body in the asteroid belt, has got a spacecraft on its way there now. So the Dawn spacecraft left the Vesta, the largest asteroid, in August 2013, I believe, and spent the last year or so traveling to Ceres. And Ceres is a very different world to Vesta. It's much larger. How else does it differ, Alan?
Well, the important thing is in its composition, what it's made up of. We knew before we got to Vesta from Earth-based studies that it was a basaltic object, in the sense that it had excuse me a minute, but it had activity on its surface. It was basically a very rocky body, although we thought it would be very dry as well. And but there's some interesting evidence from the Dawn mission that there could have been some water activity on the surface in the early solar system. But when we go to Ceres, that's a completely different kettle of fish. Ceres is what we call a C-class or carbonaceous class asteroid, or if you like, dwarf planet. It's the largest object in the main asteroid belt. And we know that it's very rich in light elements such as hydrogen, oxygen, carbon, and so on. And we really are going to a mini world there, if you like. We don't have great images from the Earth yet. We have it resolved for both a Hubble Space Telescope and by adaptive optics on ground-based telescopes. And those images they show us some surface features. But here, so you've just put up the first resolved image of Ceres from the Dawn mission as it's approaching.
Yeah, and I think they hope that in January its images will be better resolution than Hubble's as it gets closer. Its telescope on there is essentially much smaller, but I do also have Hubble's image, so I'll let me bring that up as well.
Okay, but already that we know from imaging from Hubble and ground-based telescopes. There we go. There's the Hubble image. We can see that there are markings on the surface. There are brighter areas, darker areas, and so on. And because of that, we know that this has got to be a geologically rich world, just as much as Vesta was when Dawn was there. The important thing for us, however, is that it's not just a geologically interesting world, it's probably a geologically active world as well. And this is through observations, again, with the Herschel Space Telescope a few years ago, where they actually detected water around Ceres.
And it was water plumes as well, wasn't it? It seemed to be varying with time.
That's right. The activity seemed to be going on and off and was concentrated at certain longitudes or certain spots on the surface. Now, it had been suspected previously, about 20 years ago or more, that Ceres might have some kind of surface activity, but that was never confirmed. But there was no arguing with the Herschel results, and it really is fantastic because what it tells us very clearly is that we are approaching a very ice-rich world. Something in the outer solar system that has somehow maintained subsurface or near-surface ice, or water ice, over the history of the solar system, and that actually brings about its own questions in that how is this activity triggered? What's it still doing there? Why hasn't it disappeared over the past 4.5 billion years?
And so we wait until, I think it's the middle of, or spring next year, so April. I know it had a slight delay getting there. It's it had a problem, went into hibernation, I believe, a couple of months ago, so there might be a few weeks delay. But it aims to get there in spring 2015 and start orbiting Ceres, and we'll get our first ever really close-up images of a dwarf planet, which is very exciting. But it's not the only dwarf planet in the solar system. It's the closest one, but there's another one, perhaps more famous one, of course, Pluto. Pluto's out there, way beyond the orbit of Neptune, and there's a spacecraft zooming towards it as we speak. The New Horizons spacecraft just woken up from its last and final hibernation, ready to finish off its mission to Pluto, which it passes in July, so summer 2015. And Alan, it's going to be a fleeting glimpse.
Well, it's got to be fleeting in the sense that it takes, I think, about 3 hours to pass through the Pluto system itself. But of course, Pluto's so far away and its retinue of satellites are so distant that it will be obtaining great new scientific data from several months beforehand. I think, indeed, it's about 3 months before encounter. Its images will then already be better than what we can achieve with Hubble Space Telescope from Earth or of Pluto's surface. And we know Pluto is going to be a fascinating world to visit. First of all, we know, again, from ground-based observations and Hubble, that it has very bright areas and very dark areas on its surface. In fact, it has the biggest contrast on its surface of any known body in the solar system, which is quite incredible. Another thing, of course, is that it has its atmosphere. Well, it was first detected by occultations when Pluto passed in front of background stars in the 1980s. And that came as a big surprise. And in fact, it's the only dwarf planet out there in the Kuiper Belt that's been observed to have an atmosphere so far. And the interesting thing is, again, what drives this atmosphere and what's its structure. It's been observed several times since its discovery from Earth, and we know it's very dynamic. For example, a few years after discovery, I think in the late 1990s, it was reobserved, and it was found that the pressure had actually increased in the atmosphere. There was more gas there than when it had first been discovered, which was a surprise because Pluto is now moving outwards from the Sun. And if we assume that the atmosphere is generated by the sublimation of ices on its surface, either the ice is being warmed by the Sun and being converted into gas, then that should decrease as it moves out from the Sun. So we know it's a dynamic world, and it's going to be fascinating. And in fact, the only thing we've ever visited that may be like it with a spacecraft is Neptune's largest moon, Triton. Because when Voyager 2 went past there in 1989, we saw clearly a dynamic world with a thin atmosphere. There were geysers erupting from its surface, and clearly the surface was very dynamic because we could see there are very few craters there, and that, to a planetary scientist, tells you that surface must be refreshed somewhere. How? So the 4.5 billion years of bombardment by asteroids and comets, that history has been wiped clean, as it has pretty much on Earth.
And so, I mean, you mentioned Triton. We know that, well, we think that Triton is possibly a captured Kuiper Belt object. So it formed further out and was captured by Neptune's gravity some billions of years ago. We don't know exactly when, of course. But it orbits in the opposite direction to the other moons of Neptune, which is one of the clues that it has a different origin. Now, for New Horizons, as you say, it's going to spend about 3 hours whizzing through the Pluto system, albeit with lots of images taken in advance and presumably some taken afterwards as well. And there's been a big challenge to find where next. We have this spacecraft that's going to eventually leave the solar system. It's going pretty quickly. It will never come back. It's going too fast for the sun's gravity to pull it back in. But once it's gone past Pluto, what to do next? And there are lots and lots of objects in the Kuiper Belt. We know of thousands of them. Some of them fairly large, some of them pretty small, but frustratingly, not many in the same direction as Pluto. They're all around the other side of the solar system. And that's because of where Pluto is in the sky, mainly.
That's right, yeah. I mean, the problem that the New Horizons team has faced is that Pluto right now is slowly moving out of Sagittarius, and or rather the galactic plane. And so if you want to look in the same direction that New Horizons is going, and you look around the sky around Pluto, the sky around Pluto is just full of stars. And to find an object that New Horizons could visit after it had gone past Pluto and further into the Kuiper Belt meant trying to find something against that incredible starry background. And it's not easy. Let me point it this way. We know that in the Kuiper Belt there's about one object per square degree at magnitude 24. So these things are faint, and it's taken a lot of effort. A lot of telescope time has been devoted to this project over the past few years, with a lot of major telescopes trying to find an object. And in the end, it's taken the superior resolution in the optical wavelengths of the Hubble Space Telescope to find some targets. It's found 3 so far, including this one that you're showing now, target PT1. And this target is pretty much a slap bang where you would like to go. So that's really good. Although they're using the Hubble at the moment and using its data to try and find other objects as well. So they'll make a decision over the next few months, or perhaps even after the Pluto flyby, exactly where to go. But of course, how far they can move it depends on how much fuel they've got left. And they'll be using the data obtained from New Horizons in the coming months to continuously tweak its trajectory and also decide exactly where to put New Horizons during its flyby of the Pluto system. And all of this will dictate which object it will fly past a few years later.
And there's an image up now that I'm showing of Pluto is over on the right-hand side of this image, over here, and then beyond it is this PT1, which is pretty much slap bang in the same direction. There are a couple of other objects slightly off that you mentioned, slightly off course from that. This kind of illustrates how the other big objects we know of in the Kuiper Belt are around the other side of the solar system, so not suitable for visit, unfortunately. And there's a chance, I suppose, that if PT1, which may end up with a name, who knows, is close enough to Pluto's trajectory, they might even be able to get to a second or a third object, I suppose.
That would be lovely, although to be honest, it's unlikely, because if they're going to go to PT1, then you would need to find another object even further out beyond PT1, and that would be, but it'd have to be exactly the same direction. So it's unlikely, but they're looking in those Hubble data for these, of course. So who knows? But as you say, the problem is that they can't really go to any other dwarf planets because these things are incredibly rare out there, at least the ones we know of at the moment. And so, for example, as well, Eris, you can see at the top right of that diagram, that's over 90 astronomical units from the Earth at the moment, and the Sun, sorry. So for something like Eris, you would actually have to wait another 20 years, even if it was in the right direction, to get there. So we should be happy that they've found another object. But at the moment, all eyes are focused on Pluto and the encounter in July next year.
Okay, well, I think that's brought us to the half hour, so we should leave it on that note of looking forward to more results from Rosetta, to Dawn's arrival at Ceres in spring next year, and then to the New Horizons fly past of Pluto in July next year, and results will trickle in before and after that. So it's not going to be quite an exciting event in terms of a one-day event that the Rosetta and Philae landing was. It will be a long, drawn-out process, but should still be very exciting with lots of new questions and maybe a few answers, but who knows. And we should mention that it is the AGU, the American Geophysical Union's meeting coming up this week, so keep your eyes peeled online for results from there. There should be lots of exciting results from planetary scientists around the world presenting those. So I guess we should leave it there, and hopefully we will see everyone in 2015. And who knows, we might even not be talking about comets or small objects by then. They seem to have dominated the end of this year. Who knows? So Alan, thanks very much for joining us.
Not a problem. Take care.
Yeah, and Chris had to disappear. I'm sure he wishes everyone a happy new year as well. And see everyone in 2015.